So essentially electrolysis is just going to be using external electricity to power a chemical reaction. And usually you'd be using the externally supplied electricity to force a reaction to go in a direction it usually doesn't want to go, in a non-spontaneous direction. So it's kind of like in biological systems where you're using one spontaneous reaction to provide energy to produce more ordered reaction. Okay? Electrolysis is just doing that outside of the body. So usually when we do electrolysis, we have some battery connected to the electrodes, and you use that battery to force a reaction to go in a certain direction. An example of using electrolysis would be something like electroplating. So sometimes you can get less expensive jewelry if it's just gold plated instead of using real gold, 20, 24 karat gold. But if it's gold plated, it'll still look like gold, but it really has just a 2 or 3 or 5 atom thick layer of gold on top of some much less expensive metal. So it looks like gold, but you can actually afford it. Okay, so that's electroplating. Now, how can we do the electrolysis? Some of the quantitative aspects of electrolysis, we are going to have to take into account the stoichiometry. Because the stoichiometry shows us how many electrons are needed to carry out whatever reaction we want to take place. And so the amount of the substance that's being either oxidized or reduced is going to depend on the electrons passed into the cell. Now, if you think about this, you could have a certain number of electrons passed into a cell, but what if you waited even longer? You'd be passing more electrons into a cell. So as long as you have a good battery and you keep the electrolytic cell connected, you can keep forcing more and more electrons into the cell until you're done doing whatever kind of electroplating that you want to do. The longer you keep it connected, the more reaction you have taking place. So time is going to be another component of the equations that we use with electrolysis. Now, some other constants that we might need. We've learned about the Faraday constant already. The Faraday constant essentially talks about the charge on 1 mole of electrons. And we learned that the charge on 1 mole of electrons is 96,485 coulombs. Okay. But when we're talking about time in an electrolytic cell, we know time is important, so we need a way to relate the charge passed and the time. And we do that with the units of amperes, 1 ampere, or a lot of times you'll hear people just talk about 1 amp. And we use just a capital A to represent ampere. And so 1 amp is the same as the charge of 1 coulomb per second. So when you're talking about current, you're talking about how many electrons are you passing into the system over a given amount of time. And this ampere is a unit of what we call current. And to symbolize current in equations, we use kind of lowercase script I. In physics, they'll often use a capital I for current, but for some reason in chemistry, we like lowercase italic i's. So working with electrolysis is essentially a big, long dimensional analysis problem where you have this relationship between current, which relates coulombs and seconds. You need to think about stoichiometry, so you know how many electrons are needed. And so you think about the half reaction. How much are you depositing? How many moles are you depositing? What's the relationship between moles of electrons and moles of the gold that you're plating? And then how long does it take to do that? So in your next sheet, I think the flip side of the sheet, the first problem, actually there's two sub-problems on that. We're doing an example of where we're going to look at the electrolysis of a magnesium chloride solution. So you have a solution of magnesium chloride, and you're going to run some current through this because you're trying to reduce the magnesium ions and turn into magnesium. So you want to deposit some magnesium onto some other piece of metal. So the first problem, it wants to know how much magnesium metal you're going to deposit if you have a current of 60 amps and you leave it running for 4,000 seconds. So go ahead and look at that. I'm not going to give you an equation, but through dimensional analysis, you should be able to answer that question.